first participant, Professor Adolfo García Sastre. Thank you for being here. He is Professor of Medicine and Microbiology and Director of the Global Health and Emerging Pathogens Institute at the Icahn School of Medicine at Mount Sinai in New York City. Besides all the multiple achievements, as virologist, he has contributed to investigate the development of antivirals and vaccines against COVID-19. So please, the stage is yours.
Okay.
Thank you. We're looking forward to hear you.
Okay, thank you very much, and good afternoon, everybody. Happy to be here to discuss about present and future, about some challenges in science. And first, I'm going to briefly tell you a little bit about what I'm doing and what is my research about. So I hope that is coming in my presentation here. They told me to wait 15 seconds till this starts, so I'm going to start a little bit before I start to talk, but hopefully you will see now that in the center of my research is viruses. Viruses have always fascinated me. I'm working with viruses for now 35 years. And viruses are always thought about it as the bad guys that cause epidemics, pandemics, outbreaks, and chronic infections. What we try to do through research is studying viruses in order to figure out what are the virulence profiling. Not all the viruses are virulent, not all the viruses cause disease, in order to find improved vaccines that may help against virus infections that cause problems. Immunotherapies, viruses can be used also in immunotherapy, as I will show you, and also in order to find novel antivirals. And I will cover a little bit, briefly, some of these things. So one of the things that interests me is influenza. And as you know, in 1918, there was a huge pandemic, even worse than the pandemic that we are having right now, that caused 50 million deaths worldwide and a big dip in the expectancy of life in the whole world. This is the US life expectancy. And this virus disappeared. Why it disappeared? Because it was never isolated. Why it was never isolated? Because it was not even known that flu was caused by a virus. It took forever to find, 20 years to find the causative agent of influenza, while it took less than 1 month to find the causative agents of SARS-CoV-2. But now we have reverse genetics techniques that we developed with, from cDNA, based on the genome of the virus, you can rescue the virus, and that's what we did. And we were able to sequence the virus from remainings of people that were still preserved since 1918 that died of influenza. And we actually rescued this virus under biocontainment and started to study. And what we learned about this virus, well, that was a very unique virus. There is no influenza virus that we know of that is like the 1918. And this is not due to one single thing. It's due to multiple polymorphisms in the virus genome that makes it very difficult that a virus like this will happen again. But we never can say that it will not happen again. We know now some of the things that contribute to the virulence, and that's some things that we are looking in flu viruses, whether they have it or not, in order to be able to predict some about their virulence. Now, the other interest that I have is finding which host factors are important for virus replication and pathogenesis, because these are potential targets for antiviral intervention. And for that, we have done studies together with Nevan Krogan on the SARS-CoV-2, taking all the proteins of the virus, determining the host proteins that they interact with, more than 300 proteins, and now using these proteins that most likely help the virus to replicate as potential targets for drug intervention. And we find one drug that binds to one target, that one host factor that interacts with the virus that is required for virus replication is EEF1A, and the drug plitidepsin is able to inhibit viral replication both in tissue culture and in primary cells, as well as in mice that are infected with SARS-CoV-2 and then are treated with plitidepsin or with remdesivir, which is the drug that is being in use. They have less viral replication, and they have also less disease in the lungs. So there is more pneumonia in the case of no treatment, and there is less pneumonia in the case of the treatment with plitidepsin. And this is right now in phase 3 clinical trials. We are also interested in vaccines, and we are developing actually one vaccine against SARS-CoV-2 that is based on a viral vector that can be grown like influenza viruses in eggs. And that means that there is a huge capacity to produce this vaccine that we hopefully, if it works, will be able to be distributed and produced even in countries that are developing countries. And the idea is to use this as a vaccine similar to the adenovectors And we inserted the gene into the genome of this virus, which is chicken virus, Newcastle disease virus, that is harmless for humans, and is now in phase 1 clinical trials in Vietnam, not only in Vietnam, also in Thailand, in Mexico, and in Brazil. And according to the results, we'll see whether we can move forward and come out with a vaccine that is more affordable for COVID-19. And finally, we are also using viruses to treat cancer. Why is that? Because viruses, when they have in contact with cells, they produce an immunostimulation. And by getting in contact with cancer cells, they make the tumors what is called hot, and this allows the immune system to be able to clear the tumor more easily. And that's another area of research that we are using with viruses. So by learning from viruses, we can do all these type of things. It's a very exciting area of research, especially with the new tools that we have right now for research. And I just want to finish saying thank you. And obviously, let's get vaccinated because it's the best way right now how to control this pandemic. Thanks.
Thank you very much, Professor. How interesting. We will back to you in a few minutes to keep on talking. Our next speaker is full professor at the Spanish National Research Council. She's Laura Lechuga. Welcome, Laura. She is also group leader at the Catalan Institute of Nanoscience and Nanotechnology and at Networking Biomedical Research Center in Barcelona as well. As a worldwide innovator and pioneer in the area of diagnosis and nanotechnology in the development of nanobiosensors for the detection of diseases, and during this pandemic, she focused her efforts on developing a simple, low-cost, and fast biosensor to detect COVID-19. So this is your turn, Laura. Please, welcome.
Hello to everybody. So it's my pleasure to be here to be able to share this roundtable with this distinguished with all my colleagues. But before that, I am going just to explain to you just a little bit about my research. My research that is focusing on diagnostic. And what means diagnostic if my presentation is coming, so we have to wait just a little bit. So we are going to explain, I just want to explain to you what is the status of the diagnostic just now, but especially what we have to do to achieve a real diagnostic and a more efficient diagnostic in the future. Okay, so if my presentation is coming, okay.
Yes.
So this is the future of diagnostic. I call this point-of-care biosensor and try to convince you that the point-of-care biosensing technology is the only one, the technology that can accomplish the future that we need in the diagnostic. And why I'm saying that? Probably you have seen during the pandemic, what happened during the pandemic. We have seen, that, for example, especially at the beginning of the pandemic, we have a very long lines of people just waiting to get a PCR analysis. And also they are waiting also a long time, even now, to get the PCR result. And this was mainly due because all these PCR techniques are completely centralized in laboratories. So we need a specialized technician, we need a specialized laboratories, we need a long time to get the result. So this is the problem that just today we have excellent techniques to make any kind of diagnostic, cancer diagnostic, infection diagnostic, whatever. But the main problem, they are completely centralized. So they are always centralized in a hospital, in a laboratory facility, and we have seen in the pandemic that this is having a real problem because we cannot do a massive diagnostic of 7,000 million of people at the same time with this centralized diagnostic. So what is the solution? So in my opinion, what we are trying to do, the people like me working in this area, is to offer a solution where you can make these very small devices that we call point-of-care testing devices, where you can deploy, for example, a drop of saliva, a drop of your urine, a tear, a drop of your blood, and then you put in this very small device, and then you can have a very instant diagnostic, a very reliable one. This is important to notice that we want to develop is a sophisticated machine where you can have this very fast result, but at the same time that the result is completely reliable. We call this point-of-care testing, and there is also just some few examples that are now in the market. For example, perhaps you have seen these people wearing this portable, wearable biosensor. The diabetic people are having this wearable biosensor where they have an instant diagnostic of the glucose level that they have in their blood. Okay, so my work is centering on this, in making these biosensor devices, and just making a very brief explanation what is a biosensor device, because we say biosensor means a sensor measuring a biological molecule, and this is not the definition of a biosensor. In a biosensor, it's an intelligent device where you just join a biological molecule in contact with a device, and this biological receptor, this biological molecule, is completely selective to the protein, to the DNA, to the virus, to the bacteria that you want to detect in a sample. So means that you have to join two completely different worlds, a world from the biology and a world from physics or engineering. They have to be together. We have some examples. The most famous one is the glucose biosensor that millions of diabetic people is using every day, even at home. And you know, probably all of you know this device. There is also more simple biosensor, for example, pregnancy tests that I am sure that many people have used. Of course, we have all the COVID-19 tests. We have this antigen test, this serological test. We have many other on the market. We don't have too many. So our research is mainly focusing on how are we able to produce all these point-of-care testing devices for many diseases, not only for this glucose or for a simple test like the pregnancy test. So this is one of the technologies that we develop, are very sophisticated technologies using nanotechnology and mainly nanophotonics, and then we are able to produce devices like that where you can prepare your biosensor for this, for deploying this tiny sample, blood, serum, urine, tears, and then you can have an instant diagnosis, and also you can connect very easily with your mobile phone. Okay, so this is what we are doing, so trying to do not only the fundamental science, not only the physics, how to make the sensor, but we have to make a complete engineering device where you have to join many multidisciplinary research. So we need people from biology, people from medicine, we need engineers, we need physicians, we need chemists, and this is the good thing of this research area, because we have to put all the knowledge together to be able to produce this biosensor. You can see here some of the biosensors that we are producing in my lab. Look at the size. I mean, look how in this very small chip, microelectronic chip, we are able to have even 6 biosensors or even more in parallel. And then we can then incorporate this in an instrument to do all kinds of measurements. During the pandemic, my group has been involved in one of the first funded European projects, and then we have been able to produce a biosensor for virus detection. We are detecting the complete virus. This is not an antigen test, as the one that you have done. Until now, we are detecting the whole SARS-CoV-2. And our biosensor is able to say in a very small sample if you have or not the virus, but also we are able to say how many viruses you have. And this is very important to have the number of the viral load. So we are able to know if a person has from 100 to 10 to 7 viruses per milliliter, and this is making a difference from the medical doctor to know how to treat a patient, depending on the viral load that this person has. The time to result is only 15 minutes, and we are completely selective. We have already checked to the present 2 other coronavirus, different coronavirus. And we have also developed a biosensor for serological detection as well. It's not only to give yes or not, the serological tests that are commercially available at this moment, we are able also to provide a number, a quantitative number. This person has produced this number of immunoglobulins. So you can see also in the graphic how we have the control, and then we don't see that the people have any immunoglobulin, but then depending on the pattern, we have the different levels, so we can quantify. And this is also very important, for example, for all the vaccination campaign, to know, what is the best doses for each patient. And we have also time to result in 15 minutes and excellent sensitivity. So in my opinion, and this is my last slide, I'm completely convinced that the diagnostic is one of the key points, the key steps in medicine. And in the future, we are going to need this portable diagnostic. So we need to have devices, these point-of-care biosensor devices that you can do a test in anywhere, in any time. that you can do, for example, even at home, in emergency units, when you go to see your family doctor, when you go to even to the school, to your office. And then we can expand the utility of all these technologies for the early cancer diagnostic, for allergy diagnostic, even to know if the food that we are going to eat has some contaminants. Of course, I mean, there is also a big problem with the infections, with the bacteria, and with the antibiotic resistance, with environmental pollution. So everything can be done with all this technology. And then we can't forget the concept that everything has to be centralized in a laboratory, and we need to produce all this technology. In my opinion, this is the only way that in the future we are really well prepared to probably for the next pandemic, for the next problem that we are going to face for sure. So thank you for your attention.
Thank you very much, Laura, for your explanation. How interesting. We are looking forward to hearing more of you in a few minutes. So thank you. Let me welcome now other recognized scientist. He's Samuel Sánchez Ordóñez, Catalan Institute for Research and Advanced Studies Research Professor, and Senior Group Leader and Deputy Director at the Institute for Bioengineering of Catalonia in Barcelona. He's also Honorary Visiting Professor at Harbin Institute of Technology in Shenzhen in China. Top researcher in nanoscience. His research focuses on the design of self-propelled nanobots that, for example, can navigate within the human body to transport drugs and treat tumors and other diseases. So please, Samuel, if you turn. Thank you and welcome.
Thank you very much. Thanks to the organizers for inviting me here to be in this amazing roundtable with top experts. And it's a pleasure to be in front of a young audience. I really love talking in this crowd, in this type of environment. So it's really good to have mentoring and try to explain how do we see the current science situation and how do we see the future. So I'm chemist by training. So now the challenge will be, now I'm not going to talk about COVID. So we are not working on COVID actually in our lab. So let me go back to this. So what I'm going to tell you about is about nano robotics. Actually, that's the challenge, right? So a chemist doing nano robotics is a thing that is not easy to understand, but it's full of people behind me in a multidisciplinary group. So I have to acknowledge them. First of all, it's a teamwork here. So here my title is a bit also for the audience, right? Like chasing here, like Revolution 4.0 in medicine. It's a little bit of artificial intelligence, it's materials, it's engineering, it's chemistry, it's physics, and going towards medicine. So what we want actually to do is to mimic nature. I'll tell you a lot about how can scientists copy what nature does. So here there are two videos of two different swimmers. One is a bacteria, and another one is a self-propelled nanoparticle. It's an artificial swimmer that is moving in solution. So I typically ask this to the audience, so typically people don't know how to answer, like which one is real, which one artificial. I will make your life easy here. I will tell you that this is on the right side, what is the Guinness record from our group, so that's the smallest artificial machine ever synthesized, is of the size of a bacterium. So this is just to tell you that we can do things like in living systems. But that's something that we didn't make up right now. So like many years ago, Richard Feynman made this talk. There's plenty at the room at the bottom saying that why don't we make a nanomachine and then come into the human body and cure some diseases. He got the Nobel Prize in Physics, 1965. And since then, many scientists were working, and also not science, but also this movie now. So we have science and art, right? And then we can see some movies, this classical movie for Fantastic Voyage. The senior people in the audience might remember, and more new movies like how to make tiny submarines. So imagine that you can make a tiny submarine, can go inside the body and do what they wanted to do. This will be really amazing, right? But how does a nanorobot look like? If you ask Google, Google knows everything, but here Google is wrong. So this is not possible to do at the scale. The only thing that is fine in this picture is the size. So we can do things at the size of a blood cell, okay? So, but what we do is, again, look into nature. So how nature has done many machines, robots, or things that are moving. So we are very familiar with cancer cells, but also with bacteria, with viruses, and with what you see at the bottom are actually what we do in our lab. Things that resemble what we find in nature. But now the second point is how to make this moving, and why do we want these nanoparticles to move? So the fact is that if we want to make nanoparticles that treat tumor, these need to be very efficient. And there's a current paper, a few years ago, that's very controversial, saying despite of the advances, only 0.7 of the nanoparticle designed to treat tumor reach to the target. So we need to do something different. This is, like Laura was saying, this is a problem and we need to find a solution. So our solution is to give this particle some propulsion, motion, that they can reach to the target efficiently. They can interact with the tumor matrix. They can penetrate. They can talk to each other. They can collectively move. So the way we do is, in another way, will be like changing from passive to active transport, okay? But at nano scale, this is very, very challenging. I'm not going to go into the details on how challenging it is, but here you can see a video on one side, a particle that you put in solution, this is not going to move. On the other side, you see a self-propelled particle, okay? And the way we do this, we take a particle and you put enzymes, these enzymes and catalysts we find in our body, and you can take a substrate, then catalyze the reaction and move the fluid around and push the particle forward. And if this substrate is in our body, that will be ideal. So one ideal body fluid will be blood, but this has some challenges. But urine has a big component, which is urea, and urea is taken by the urease, and we make this reaction, okay? Anyway, I'm not going to, again, go into detail, there's a chemical reaction makes a chemical flow here. But life is not about individual people, right, and about individual phenomena. Life is full of collective phenomena, how bacteria, how viruses invade, how birds are moving, or how sperm cells go to the egg, right? This is collectively. So that's how the future is going. So in the last 5 years, we managed to get a particle moving in solution to make it fully biocompatible. Now the challenge is how to understand from individual to collective. Okay, so if we want to put it inside the body, there was an article which says we need trillions of nanoparticles. How to make trillions of nanoparticles, how to put them inside the body, how to make them move, this is a challenge, as I said, for the next 5 to 10 years. So far, what we do is things that move, they can reach to 2D cells, they can reach tumor cells, they can reach spheroids, which are 3D structure, similar to a tumor. And also, in the last year, we managed to see them in vivo in a mice bladder. So from the bench to the clinic, how far we are from this? So what the first thing we need to do, scientists, is to copy, to do exactly the same protocols they do in the clinic, right? So what we do is we inject into the bladder exactly the same protocols, we inject these nanorobots, and then we bring the mice to the PET CT, to the imaging technique, and we see what happens. And then what happens is these nanorobotics are moving. You see this red cloud, these swarms moving all around the bladder so they can reach to the whole wall where the tumor is. So we make a treatment which is very, very efficient, much more compared to the typical treatments, like immunochemotherapy, where they only get to one side of the blood. Okay, so where we are, where we're going now. So nanotech, what for? So many years ago, this was emerging, right? Then it's not only doing nano, but it's using it for something. We need to look into nature, inspired by what is around us. We are finding some applications, not only medicine, but in our group we are doing environmental application, how to clean water. We are doing sensors as well. We come from the same school as Laura from the biosensor group, and for the future. So what are we doing is combining materials, physics, chemistry, also all the way to medicine. For you, we're going to talk about this now in artificial intelligence. So now there's a lot of data there, so we want to do something that needs computer vision, robotics control, mathematics, and etc. So thank you very much.
Thank you, Samuel. Thanks very much for your introduction. We will back to you in a few minutes. Our next panelist is Susana Marcos, who is meeting us online. Hi, Susana. She's David R. Williams, Director of the Center for Visual Science, Nicholas George Professor of Optics at the Institute of Optics and Professor of Ophthalmology, Flom Eye Institute at University of Rochester in New York. As a physicist pioneer in visual optics, she was recently appointed Director of the Center for Visual Sciences in Rochester, an international reference center in vision research, with expert in optics, neuroscience, bioengineering, and ophthalmology. So please welcome Susana. Would you like to tell us something about your specific work, please? Welcome.
Absolutely. It's a real pleasure to be here, and actually it's a real pleasure to have this event in my hometown, Salamanca, where I grew up and where I went to college. So maybe you can have my presentation where I can, and I will be discussing a little bit of our research our research that actually is about how to be able to see better, and the light. The light that comes from the world hits our retina, right? And it's projected by part of ourselves that allows us to see light, but also to see colors, to see shapes, and this can go wrong. And what my lab does is really how to understand how the eye works, and how we can fix it in conditions that are very, very prevalent. So the eye is this fascinating tool that we use actually optical technologies, much like the eye itself is, to investigate. So we use light sources, we use optics to really understand the optical properties and the image forming capabilities of the cornea and the crystalline lens, and how these images that are projected by these lenses are sampled by photoreceptors in the back of the eye, and how this information is actually going all the way to the brain and interpreted. So the eye, being as exciting and as fascinating as it is, has some imperfections. So one of the earlier technologies in my lab was actually inherited from astronomy, where ground-based telescopes are based with wavefront sensors that allow to measure the optical turbulences and the imperfections of the light going through the atmosphere. Well, we do that for the eye to characterize the errors of this eye. And this can go up to many different terms. Probably the most well-known and the most important are refractive errors, like myopia. And myopia, it's a condition that affects 30% of the population in Western countries. Some countries, some Asian populations, up to 90%. In Hong Kong, in Singapore, is really a pandemic for myopia. So we're actually having the tools to understand why myopia develops, and also how to correct it. Interestingly, visual impairment due to uncorrected refractive errors affects over 100 million of people worldwide, and it has been identified by the World Health Organization as one thing to really take care of. In fact, you can improve the quality of vision by providing someone with glasses, and in fact, eyeglasses are one of the most cost-effective healthcare technologies. However, the simple prescription of getting the eyes into a person requires random optometries. There's one optometrist for 6,000 people in Western countries like USA or Europe. But you go to rural India, there's one optometrist every 250,000 people, one optometrist per 1 million people in some parts of Africa. So when the eye doctors come to a village once in many years, there's these long lines that are formed to get a prescription. What, in collaboration with MIT, we did a few years ago was actually to develop a low-cost auto-refractometer that is actually based on these wavefront sensors that we're taking from astronomy, but actually brought into a device that can measure at the click of a button the prescription of an eye. So that's made into a clinical instrument and a commercial instrument by Planoptica, based in Boston. It's called QuickSee and provides accurate refraction everywhere. So we're bringing these refraction measurements to virtually every part of the world very accurately. So we have these corrections, these imperfections like refractive errors. There's also other higher order aberrations, up to a few dozens of aberrations that we can not only measure with this technology, but actually correct with similar tools that are coupled with ground-based telescopes to make the images of the universe sharper. So what we can do is we actually can do the images that are projected on the retina really sharp, sharper as anyone can have ever seen. And we can actually play and put someone's eyes and someone's imperfections in some other person's eyes. We can mimic different corrections, and we can really explore how the brain interprets the images with new optics. And this is very relevant for corrections. It's also very interesting to understand where these imperfections come from. So we have developed 3D, fully quantitative biometry tools, anterior imaging systems, where you can see here the cornea, the crystalline lens, maybe an intraocular lens implanted in the eye, very accurately and very quantitatively. So we're shedding light into changes in the eye occurring with normal processes like accommodation. So what happens inside the eye when you're focusing near or far, what happens with the crystalline lens, for example, when refractive errors, when myopia develops, and what happens with aging. And there's at least two conditions that are really prevalent that occur with aging. So one is presbyopia. This is the crystalline lens losing its ability to focus, to accommodate, and this affects 100% of the population over the age of 45. This is 1.5 billion people worldwide. Or cataract, which happens later in age, around 65 years of age, half of the population is affected, where the crystalline lenses loses transparency. Interestingly, cataract surgery is the most performed surgery in the world, in any hospital in the world. There's 28 million of cataract surgeries per year worldwide. So we're developing these tools where we can now simulate visual correction. So going from the lab, from these adaptive optics based from astronomy, visual simulators like bulky instruments very sophisticated in the lab, going into something that is wearable, head-mounted, and binocular, we are actually now giving the patients the experience of how a given correction in the eye is going to look like a new intraocular lens, for example, to correct for the presbyopia or cataract. And again, this is one other system that has made all the way from the lab into the clinic. This is the Synvis, developed by our spin-out company, Twice Vision, that is actually changing how intraocular lenses are prescribed and how cataract surgery is offered, and also contact lenses are offered to patients. Learning and really understanding how the eye works has led us to mimic some of the features of the crystalline lens in the young eye, or to develop different modalities of intraocular lenses. So, for example, we have produced multifocal intraocular lenses that are now implanted in many people around the world, over 50 countries, these, which we believe are the intraocular lenses of the future, truly inspired by the crystalline lens that change the shape to produce accommodation. But we're now producing these lenses that have the same capability, that can accommodate, that can change their shape to focus dynamically, and actually restoring vision to the properties that the crystalline lens has in a young age. So in summary, we're using optics, we're using light, we're based in a very multidisciplinary program where neuroscientists and optical engineers and biomedical engineers and chemists and ophthalmologists and optometrists work together to really increase eye care access, to improve cataract surgery, to restore visual function. In other words, we're using light and we're using the knowledge of optics and multidisciplinary understanding of the visual system to improve vision. So I want to thank you all for your attention, and I'm really looking forward to discussing pressing topics in research with you and the prominent scientists in the roundtable. And I thank you very much for your attention.
Great. Thanks to you, Susana. We'll back to you in a few minutes. And last but not least, we have one more panelist. She's Ángeles Gómez Borrego, Vice President for International Affairs at the Spanish National Research Council, a geologist fighting against climate change with several projects around the world. She worked in the clean utilization of organic components in industrial processes at the Institute for Carbon Science and Technology in Oviedo. So please welcome Ángeles, this is your turn.
Thank you very much. I feel really honored to be here today to share the roundtable with so prestigious scientists and to be here in Salamanca, a town that I really like. You have a wonderful town here. I was told indeed to talk about my research when I came to this roundtable, and I thought that I will talk about my path, because I think that this might be of use for some of you scientists, young scientists who are deciding or have to decide in which area you are going to work. And I will show you what was my experience in my work, in which I move or migrate a number of times of research topic, and nothing bad happens. So you don't have to be right from the beginning in your decision, or you don't have to stick to the first decision you take in your process, in your career. So when I started to work, when I started my PhD, which was quite after the time you are starting, I was working with something that you really wouldn't like to listen now. It was petroleum source rock. Nowadays, we don't want to listen about petroleum because petroleum is dirty, because petroleum is producing greenhouse gases. But at the time, it was 30 years ago when I started, and I don't feel so old. It was just at the end of the last century. That was a hot topic for the petroleum industry, where we have to put together the characteristics of the source rock and the oil, because you usually don't have together these two parts of the binomy. So, and it was important, it was relevant to have good correlations between parameters you could extract from one or another rock, another stuff, in order to try to find good source rock oil correlations, which were helping in the oil exploration. You think I can have the...
Yes. You have to...
Oh,
yeah.
okay.
Great.
I have to do myself. Okay, this was an example of the kind of molecules we can find in the oil, these complex organic molecules, and how the organic matter you have in the rock is looking like. Afterwards, this was the first topic in which I was working. Afterwards, I moved, after returning from Germany, I was coming into a group which were dealing with improving the quality of products coming from coal utilization. Again, coal, something we don't like nowadays because it has the memories of dirty stuff. But it was very relevant to try to optimize the coal quality in the steel production, and it's still something we need to do to try to study and to optimize the reactivity of the different components we see in this pink image with different colors and different shapes, and the distribution, the size, the position determines the quality of the coke in the high oven. In the same way, when we burn coal, we can have different structures which are responsible of the final efficiency, and we can act on these parameters, on these variables, in order to optimize the process and minimize the amount of unburned carbon in the ashes. If you optimize the process, you are saving energy. If you optimize the process, you are taking care of the environment because you are having less residues at the end. At that moment, when we were working or busy with this, it became clear that the fossil fuels were producing massive amounts of green gases, and therefore it was necessary to stop to produce from coal or fossil fuel utilization these green gases, this CO2. Then we were working in different technologies for trying to mitigate this CO2 release to the atmosphere. And this, I must say, it was something like 10 years ago, 10, 15 years ago. It was a golden time for the clean coal technologies. Everybody tried to find different solutions because at that moment the scientists and the technologists were really sure that only producing or deploying clean coal technologies was going to be the solution to really fight against climate change. Luckily, the wind energy, the solar energy, went faster in the research, and this is something also which is important to stress, that we need to explore different solutions, we need to explore different ways to address the questions, to address the problems in a way that at the end we will be lucky with any or with some of them or with many of them, which will be the winners, no? Will be the last ones which will be in place. No? Well, after that, I turned back because at that moment it was already clear that climate change was one of our worries, and that we need to find solutions for that, but also we need to find evidences to support all the changes we were already observing. So these models needed to be more robust and needed to be more solid. Then we went back to the origins, to these organic geochemical studies, and we applied this formation, this background in the study of peat as paleoarchives in order to reconstruct the climate in the last 10,000, 12,000 years. So this brings us this kind of studies. I was working in peat, but other people were working on ice cores or on tree rims or on coral rims. So there are many, many ways to address this question and to find for how was the climate in the past where we were not able to measure direct measurements. And as an example, I show you a couple of conclusions from the previous IPCC Intergovernmental Panel for Climate Change conclusions. And in 2014, it was written, it is extremely likely that the warming observed in the last 50 years is due to anthropogenic input. And just 3 weeks ago, the last report came out, and all the work that the scientists have done in this period has been translated into this unequivocally due to the emissions from human activities. So this change between extremely likely and unequivocally due is due to an enormous amount of studies, an enormous amount of data treatment to put them together. So now I am more in management activities, and believe me if I tell you that we are really worried in trying to put the information the scientists produce in a way that the stakeholders, the politicians, are able to understand and to in order to take the measures to help our planet and ourselves in the future. Thank you.
Thank you, Ángeles. We will start now with the roundtable, but before starting it, let me remind you that if you want to make any questions to one of our scientists. And if you are watching us through the virtual platform, you can use the hashtag Eucys2021 to make one of those questions. So shall we begin with the roundtable, if you don't mind? So the first block is climate change. I would like to start with Ángeles, for example, if you don't mind. And I would like to ask you how important is to know the danger climate change can cause in our daily life, and how science can fight against it and improve the society, if it is possible.
I think, it's very important, clearly, that we know how this climate change can affect our society, and that we can measure also, we can give quantitative data on how it's going to affect. Because if we talk about, it's going to be very dangerous, it's going to be terrible, big disasters, so more frequent floods, more fire. It's true. This is going to happen because this is something which we are already realizing.
Because of the climate change directly.
Because of the climate change directly. This last report is clear on that. So the extreme events are directly caused, the abundance and frequency of the extreme events is directly caused by the climate change. So but it is also important that we take into account that it's not only the climate what is going to change. There are a lot of things which are affected. Our way to feed ourselves, our way to produce the food. So there are a lot of research needed in this area of new aliments, new foods that can be produced with less water, in more extreme conditions which are not appropriate for the species we have right now. There are going to be migrations that we have to take into account because of the climate. So there are a lot of things, not only the rise on the sea level, which is something which is very evident and is probably the first thing which is going to affect, but there are going to be much more effects in the society, and this is also going to be very expensive to solve that. So to have this cost of this disaster in the equation may help the stakeholders to decide that taking the measures, which are also expensive, to stop the climate change might be more convenient than solving the problems created because of that.
That's why we have to be very conscious with this time. So, Susana, for example, I think you can listen to us. How do you think climate change has to be considered in science projects?
Yeah, well, that's a question that it doesn't relate to my specific field of research, but I think something that has been clear from everyone's presentations is how connected research is across fields, and how research these days is fully multidisciplinary. I think we've heard from Samuel linking robotics and biology and medicine. We've heard from Laura about bioengineering, but with an application in medicine. So I think all of these fields are connected. So what I would say is that in everything we do, and in everything, in every research field that we cover, and everything we do in our daily lives, everything is connected, and everything can have an impact on the environment and on climate change. We all need to put resources into that, and we all need to think in the products that we may deploy as part of our research, to be conscious about sustainability. And I think in my area of research, we're working and thinking on like green chemistry for the biomaterials that we use in the eye. We are conscious about sustainability of the tools that we use in surgery. So all this, I think, is very important to have in mind, that everything is connected, and that everything that we do may have an impact in fields outside, and protecting the environment and protecting the planet. The planet should be a #1 priority for everything we do.
Adolfo, do you want to add something?
Yeah. Following on that, so I think it's a great point that she made, right? Like, be open and connect all the ideas, and open to serendipity, right? So I actually was invited to this European summit that, the summit that you explained today, right? And from Madrid, there was another parallel about European Council. So I was presenting part of my work on nano robotics and how can we clean water. So it was not planned to do that, but you see things moving, things that can generate, because of chemical reactions, something in water, and you can clean, right? So why not to use it and invest some money? They convince the stakeholders that any science, not that the one that do only geology or any other department from our departments can be used for society, right? So water is one of these, right, sustainable and development goals, right? We need to be very careful in the future, because there will be less water in some countries, right? Drinkable water. So use technology and new materials to clean it. That would be one of the main points, right? So be open to that and connect the ideas.
All the areas has to be connected, Laura.
Yes, what I want to say also is that, of course, science can provide many answers, and then we can be all connected all together. And science has already demonstrated during this pandemic that we have been able to solve the pandemic due to science. And I think this is the same for the climate change and for all the environmental issues. Science can provide the answer. But the problem is that we need the involvement of all the society. We need the involvement of the politicians, the stakeholders, and this is the problem for us. We can do many things in science, but of course we need the involvement of everybody. It's not only the scientists that we have to just to fight that, to say, okay, we can do that, and we can solve this and this, but we need, of course, the support of all of you, of everybody, of the society, and especially the politicians, because it's the only way to stop this big, huge problem that we have. Because this pandemic was also related to the problem with the climate change, with the environmental issues, with the forbidden habitats that we are just entering. So we have to be aware that we have a huge problem, and it's the time to solve it.
We will talk about pandemic, but it is
related.
There
is actually a very clear impact of climate change in epidemics,
the epidemics,
which are especially those diseases that are being transmitted by vectors, the mosquitoes, that are an habitat that is in tropical and subtropical areas. I'm talking about Anopheles that transmits malaria, and the Aedes mosquito that transmits chikungunya, dengue, yellow fever, and Zika. These diseases have been confined into tropical countries, but because of the expansion of the habitat of the mosquitoes that now can reach to regions that become now with a climate that is more moderate, now we are seeing dengue cases in areas of the world where there were before no dengue cases. And that's because the mosquito has arrived to these places, because now the climate is more favorable to the mosquito. So there are all these consequences of climate change in terms of economy, in terms of resources, in terms of infectious diseases, and that's something that is one of the clear problems of mankind that needs to be solved, and the science needs to play a major role in solving the problem of climate change.
It's all connected, isn't it? Then we will talk about pandemics, and I will introduce a new blog, which is artificial intelligence, and I think it's quite important to be focused on this point because, for example, Samuel, I would like to talk about the importance of the study of data, big data. How important is that in science? Because nowadays we see every day a big amount of data. And how can we use this information, for example, to fight against climate change, pandemics, etc.?
Well, in terms of artificial intelligence, I think we should divide in two blocks, right? Like the software, the big data, the analysis, right? All the algorithms and the hardware.
Stuff,
Hardware will be more the robotics itself, the humanoids, like the big machines in industry, right? So either one or the other that will be in the future among us, and it's clear they're right now here, right? But regarding the data and connected to the pandemics, right, they will be, and in the daily life of our research, we're creating more and more data, right? There's more sensitivity in the machines, where we're creating something that, well, big computers that we can accumulate a lot of data, and we need to understand very quickly. We need to be very agile also, not only in the company using these words, right, but using in science to interpret this data, right, and analyze it, and also predict what's going to happen in the future. So we need to keep predicting what's going to happen, the climate change, right, and this is thanks to analysis, artificial intelligence, machine learning, neural networks, making them learn themselves. So my suggestion for everyone here in the audience, whoever is listening, so we keep seeing these more often in the CVs. So I have no idea about algorithm, I have no idea about programming, but that has to be a must, right, in every CV when we see it, because they need to have at least some hints and some background, some knowledge on that, because it's going to be in the daily life in the future, right? So very, very, very important. Right?
And talking about robots, for example, we have one of the first questions our students have made us, for example, for Professor Adolfo or Samuel. They say, what are the advantages of nanorobots in comparison with, for example, receptor-targeted cancer treatment methods?
That's a perfect question, actually. Like, so we talk about vectors, about particles that can transport drugs, right? And these particles cannot, let's say, drill into tissue, interact with extracellular matrix, right, or reach to the target efficiently. So, of course, you need. So, in our case, we also have antibodies to target. So we're doing is to help in this short-range interaction. So when you go to a tumor, there's interstitial flow pressure that pulls the particle away. So if you have enough force to penetrate this, interact, and also I like very much what you said, right, about the viral, like with the cells, and the respond to immune system to make the cells interact with these artificial systems that we put there. So the advantage would be the cell propulsion and the interaction. We have demonstrated that you can drill much better, penetrate into cells, tissues, and tumors than something that doesn't interact with it.
Yeah, and it's not only a question of advantages or disadvantages, it's a question of cooperation between these teams.
Yeah.
You can use advances in technology to take all technology and then make it better. So that's the beauty of all the tools that they have now in science.
Of course.
And you know, we are in a very exciting times in science with all the things that we can do, all the information we can get. And actually the challenge is how to use the information in a better way with all the tools that we have in order to make really impacts in the big things that happen, like is quality of life, like is climate change, like is trying to get and to stop the next pandemic that it comes.
And I would like to know as well, how has artificial intelligence, for example, has changed the science, and if science has changed the artificial intelligence, so something like vice versa. Any of you? Yeah.
Well, as I said, like maybe 5-7 years ago, let's say 7 to 10 years ago, when I was in the lab, like still analyzing my data, well, by clicking, video by video, very slow process. And now all my group members, they just get a lot of videos, a lot of data, and they can easily, in a couple of hours, analyze what I was able to analyze in 1 month. So these algorithms are helping there, of course. So the way without this, let's say, the swimming intelligence, this cooperative intelligence that I'm just proposing here, right? We cannot think about any application in the future. So then the robotics, whatever is happening in the industry, like the robotic system, how things cooperate and the robots can talk to each other, this is something that they are much faster than we do at the nanoscale, so we need to learn from that. So everything is moving so fast. What we should not do is to stick to our own problem, our own technologies. That's what we're doing here, right? Like listen to each other and try to get some ideas that I'm already getting from each of them, and from the question, of course. Listen to the question that every time, like I have questions from the audience, like I go back to the lab and my people suffer, like, oh, there's something new that's going to happen here, but things will change very quickly, right?
Talking about technology, we have another question, this for Susana. Susana, our students say that, do you consider that cellulose layer are a promising way to treat eye injuries?
Well, that's a great question because, I mean, it's not cellulose layer, but another type of biomaterial coming from nature is actually the topic, the central theme of our new ERC advanced grant called Silk Eye. So yeah, it's the standard of care right now for wounds in the cornea is actually putting an amnion membrane on top of the cornea to favor the wound healing of an injured cornea. But by placing other biomaterials that are readily accessible in nature, and this is what we are doing with silk fibrine and polymers based on that, we're actually being able to recreate what you can do with this amnion membrane. But now this is not allergenic material. It's readily accessible. It's affordable. So yeah, looking into what nature can provide us and harness it to our interests is, I think it's very important in many different research fields, and we're using it for the question of healing the cornea, as the person that made the question suggested. So, yep.
Talking about these things about how technology changed everything, do you have any pieces of advice for our students, for example? Because I think they have to be very up to date with everything. So, do you have any advice to give them? Just to say, you have to be, or do you have to know everything, because things change every day. So, for example, Laura, have you got any advice of this stuff?
Well, this is difficult, but of course, I mean, it's not possible to know everything.
Yeah.
So, and sometimes it's better just to try to focus on one thing and to be an expert on that, and then to try and not to try to, to know just small pieces of everything. So my main advice is, if you want to do for a scientific career, is that you choose what you like more. I mean, you can go for pure science, you can go for engineering, you can go for chemistry, physics, and so on. But just try to, to have a very strong background on that. And after that, you can specialize, you can do many other things, even if you are studying physics or chemistry or whatever. It doesn't matter, because all of us, for example, like Samuel and myself, I have a background in chemistry, a PhD in physics, and then I have been working in engineering, in biology, in medicine. But it's better if you start having a very, very strong background, at least in one discipline. And after that, you can specialize in what you like more. I mean, if you can use physics to do medicine, you can use technology to do environmental studies, whatever. So my main advice is not try to cover everything. That's not possible for nobody. But my main advice is first start having a strong background in one discipline, the discipline that you like much more. And then after that, then you have time to also to find where you can do this multidisciplinary, you can acquire a multidisciplinary knowledge by yourself, but depending what you like more and what you like to focus more.
We had another question, but maybe we have to keep on talking about, because we have lots of stuff to do. So the third block is pandemics, which is related, for example, with climate change. We used to talk before. So, Professor, for example, you've been working on improving everyone's lives during this pandemic. You have research on the development of antivirals and vaccines against COVID-19. So, will we have to deal with new pandemics in the future?
Yeah, unfortunately, pandemics are not finishing with this one. You
mean that this is just the beginning, or what?
No, not the beginning. It's just the continuation of a long history. If we are lucky, our generation will not see another pandemic, but sooner or later another pandemic is going to happen. And, it's not only pandemics. There are specific outbreaks that can cause a lot of problems in a specific region of the world. Outbreaks of Ebola, outbreaks of Nipah virus, multi-resistant bacteria that may become little by little, not sudden, like happened with these pandemics, but little more prevalent, and then causing more disease. This is something that we are going to need to deal all the time. There is a lot of biodiversity in the world, a lot of viruses lurking that sooner or later they are going to evolve a little bit and then going into us. That's happening all the time, often. Not so much in one generation, but over several generations, a big pandemic happens. And the question is to be ready for that. And it's not only science. It's always a question of the society being prepared to deal also logistically when these things happen. But in terms of science, it's clear what we need to do. We need to find much better what is around in order to be more aware of the dangers, find treatments that are more broad spectrum, that will be able to cover not only specific pathogens, but multiple pathogens and multiple families that target conserved areas in pathogens that belong to the same family, and some of them may have never caused pandemics, like what happened with this coronavirus that came, and vaccines that are, again, more broad spectrum, that will be able to cover not only one single pathogen, but if we target regions that are specific for families of pathogens, then we will be better in terms of having at least weapons that are for the treatment and prevention of the new things that come. And then in terms of prevention, there is a lot of things that also need to be done, and that science can help on that, like what is the best way, how to contain things to prevent jumps from nature or from wild animals to domestic animals to people, which is how these things happen, how these new viruses come in. It's not that they are suddenly coming from nowhere. They are somewhere, and then at one moment they get in contact with a human. And if it is the right circumstance for the virus, then it's when the virus comes, and that's what it does, like this COVID-19.
Mm-hmm. Laura, do you think we can do anything, if it's possible, for try to avoid new pandemics, or if it's impossible?
No, I mean, it's possible. I think that one problem also with this pandemic is that we forgot to do all these surveillance studies that we are doing for the evolution of coronavirus, because as you remember, we have already another coronavirus a few years ago, the SARS-CoV-1, and after that they decided just to do all these studies using all the diagnostic techniques to do the studies of the surveillance and to prevent future outbreak, but then it was stopped by the politician, of course, and then there was not enough resources to continue. But now we have to be completely aware that we need to be controlling what is happening, because we have thousands of other coronavirus that can eventually just go into the human. So we need to develop all this diagnostics technology that you are able to make a very early diagnostic, and also to make all this early surveillance of any outbreak of any coronavirus that can jump again to the human people. And also, as Adolfo said, we have even now suffering what we call the silence pandemic, and the silence pandemic is due to bacteria. We have now the problem that the bacteria, which are very intelligent, they are mutated in such a way they are destroying all the antibiotics. We don't have almost now, there are all these super bacteria that are able just to, we don't have any antibiotic against this bacteria. And we have some prediction that by the year 2050, is going to be more people that are going to die due to this super bacteria than to cancer. And this is the number. So millions of people are dying every year due to this silence pandemic. So we have to be able to produce new diagnostic, a very early diagnostic, to know who is getting infected, and then to try to give a treatment as soon as possible. So this is something that, of course, diagnostic and then treatment and then vaccines, everything have to be together. But we have to focus on that because we are facing huge problem for the future.
Talking about diagnosis, for example, we have another question for Professor Adolfo. One of our students say, are you telling us that it will be a vaccine for cancer?
It is not so outrageous to think about vaccine for cancer. Therapeutic vaccines, there is a lot that is being talked about potential therapeutic vaccines against cancer. But, the vaccine against cancer is, even before cancer appears, can you get vaccinated against cancer? And in fact, we have a vaccine against cancer, which is against papilloma. Cervical cancer and some of the cancers that are caused by papillomaviruses, we have now a vaccine that is able to prevent papillomavirus infection and therefore prevent cervical cancer. And in the future, if we know better about what antigens the cancer cells have that are specific for cancer cells, that happens in cancers that are common, or we can predict what person will likely to have a cancer that has these particular antigens, if we know that, then we could, in theory, be able to make a vaccine, the same thing that has been done for papillomaviruses. So it's not so outrageous, and I think hopefully I see it in my lifetime, but it's up to the young people that are right now starting to do science to go and then doing the real job and then finding these things.
Samuel.
Yeah, this is something very nice, and this type of personalized medicine, right, for the future as well. So if you can, we can get also cells, tumors for patient, and understand this with the antigens that are expressed on each type of patient, and then develop these particle robot or vaccines, right, almost on demand, not for each of us, but for subpopulations, and that will be more specific for the future. I think this is possible. It's here, right? It's available, but we need to listen and empower to scientists. That's my statement connected to what you said to us, to Laura, right? So probably many of these things and the future pandemics and the future disease is something that we might know and might be around, but we just need to listen to us, right?
It's probably not as simple as I say, but the principle is there.
Yeah.
And the demonstration of the principle is there with the papilloma cancer vaccine, the cervical cancer vaccine. So the principle is there. It's a question of using the resources that are needed in order to understand much better this concept and then coming out finally with solutions. Not today, but hopefully in the future.
We wish. We are running out of time, but I would like to introduce the last of our 4 different blocks, which is pseudoscience. And, for example, Ángeles, I would like you to say something about, for example, we are talking about vaccines, we are talking about virus, for example, and what do you think about, for example, anti-vaccines people or different opinions?
Well, if we talk about pseudoscience, in 2 words, I would say pseudoscience, no, thank you.
It's a good resume.
Yeah, this is. We can take the slogan of the nuclear against nuclear energy for this, because I think it's really dangerous. No, it's a collection of statements, beliefs, practices which are not based on science, but claim to be based on that, and therefore is particularly dangerous for that. And then with vaccines, of course, is the same story. No? They are feeding this feeling that and explaining, probably you know better, that are so problems with the vaccines, with any medication or whatever, which is going to cause disease or problems greater than the ones to be solved, which is not true, is not based in any scientific record, scientific proof, but is said, and there are always people who believe that.
Have we always have pseudoscience, or is it something new or something, no, Laura?
I would like to say that, that these people, that they don't believe in the vaccine, they don't believe they think that this is not true. They should think, 100% of all the scientists in the world, all of us, we are completely in favor of the vaccine. We are completely in favor of developing treatment, on diagnostic, and we are trying to manage this pandemic. We are completely in favor of vaccine. So, I think these people have to think, if we are the experts, and the 100% of the experts are all around the world, all of us, we are completely in favor of vaccine.
Yeah, they are telling the same thing.
They should believe us, and they should believe that we are the experts, and all the experts are saying the same. So this is, I think, the best demonstration that the vaccines are working, and the people should think that we have been educated, we have been spent so much time of our life, just in science, and if all the scientists around the world were thinking on that, that the vaccines are the correct way to control the pandemic, they should believe us.
Mm-hmm. Yeah, I think the main question is here just what the data says, right? And it's very clear that vaccines are saving lives. You just need to see the data, what is happening in places where there is vaccine use, what is happening in places where there is no vaccine use. So there is no question about it. I think one important consideration that we need to do with pseudoscience is first that science is not perfect. We as scientists can be wrong. There is a lot of debate in some areas and some theories that are different from others, and that's actually healthy. Someone thinks that with the data that it has, this is the interpretation that it has, and someone else come. I'm not sure that this is the interpretation because I think you are missing this point. This is healthy debate, but there is some other debate that is there are so much data that says already that this is actually of benefit. That is, and that's the question I guess for the general public is how to distinguish between things that are still debatable among scientists, things that science don't know, scientists don't know at this moment, and things that are actually fakes,
future,
right? Fake science is thing that does not have any scientific evidence that happens like that, and not only that, but all the data contradicts anything that is based on a theory like the vaccines are not working, or COVID-19 doesn't exist. This is also some of the things that we can hear from here and there. But there is no virus around. It's just what they want. Scientists want us, and politicians want us to tell that there is a virus around to control us. Well, it's a pity that some people think like that. I think it's mainly a question of education. I think it's not easy to solve, but hopefully with more education in the future, these type of things are less and less prevalent.
Yeah, just to finish, because we are running out of time, I would like you to give, as Laura did before, a little advice for our audience, our young talent. So in a minute, for example, each of one of you, I would like to give them a little advice. For example, we can start with you, Susana, if you don't mind.
Yeah, so what I would say to everyone is just follow your passions. I think no challenge is too big if you really believe in what you're doing and you really have, the power to undertake it. And also, use all the opportunities that are around you. So I think it's not only luck. It's really catching the opportunities and make the most of them to learn and to interact with the people that can guide you and getting help from others. But really, if you have a dream and you have a passion, there is something you want to investigate and change the world, go for it.
Great, thank you. Ángeles, for example, your little advice.
Keep on learning and don't be afraid to be wrong. Just keep on trying.
Great advice. Samuel?
Well, I was always talking about passion in my talks in the past, but now to don't replicate, it's make the best out of your time. So use all the opportunities we have out there and don't waste your time. Like go and visit. This is a global world, and the knowledge, the information, the data is out there. So you have a lot of time over summer. You are very active students, right? So go to one lab, go to another lab, and find these patients, right? Like whatever you love. Maybe you don't know what you love, but you'll find it on the way, right? And be very active as all the students who are here are extremely active. If they are here, they're on the right path. So, probably they don't need too much advice, but enjoy your time. Yeah.
Laura, shortly, have you got any other advice?
Just my advice is, we need more scientists. We need a lot of science in the future. And especially, I want to give a message to all the women. We need more women scientists. So please, just all the women, we can do a great work. And then please believe in yourself.
And at least, Professor.
Yeah, I think it's clear. Follow your. You see us. You can see that we love our work, and despite all the frustrations, there's a lot of frustrations in science, but we scientists, we love what we do. And there is not so many professions that you can say, I love my work, and science is one of them. So if you feel science is your vocation, you have the talent, don't waste your talent, just go for the science, follow your passion. It's a job that you will find that you love it, even despite all the frustrations. And that's great in life. And also, you do something for society. It's a great job.
Thank you, all of you, for this inspiring conversation and all the advices. I hope our young audience has enjoyed it as much as I did, and of course learned from these professionals who are some of the most prominent scientists in the world. And indeed, that's one of the main goals of this event, to feed your curiosity, and that's why we gave you to our contestants and our on-site spectators a very special gift as a metaphor of this spirit, a tiptoe. I don't know if you know what it is. Some of you will be wondering what a tiptoe is. It's really easy. It's a toy that, when spinning, spontaneously inverts to rotate on its own shaft. The phenomenon of the tiptoe has fascinated the world of scientists since the 1800s, including Nobel laureates such as Winston Churchill, for example, Niels Bohr, Wolfgang Pauli. The fact that when the tiptoe inverts, it also changes the direction of the rotation. The same effect, for example, can be accomplished with an American football or a hard-boiled egg. We have a video in which we can see this effect, for example, and if you can read, this video shows how to distinguish a boiled egg from a not one. So if it turns normally, it is a crude egg. You can see it. But if when turning, it stands on its longest axis, it is a boiled egg. This simple object, this tiptoe, summarizes the messages behind this contest, Eucys. The first of them is stay curious. Why does the tiptoe invert it in its spinning? The answer is in science. Everything is science. We have been talking about it. And secondly, teamwork in science. Laura said before, teamwork is absolutely required. As an example, for example, we were watching that photographs. Niels Bohr and Wolfgang Pauli were found discussing about the physics behind the tiptoe spin. So it is a nice story, isn't it? Now it is the time to say goodbye. I would like to thank our viewers for watching us and for the passion about science. You are a seed of our future. I will take this time to thank as well our sponsors. Your support to this event is key to keep empowering young scientists. And thanks again to all of you for being here with us this afternoon. And remember, tomorrow we will get to know the winners of this contest. So do not miss the award ceremony to find out who are the winners. So see you tomorrow. Thank you very much for being here, for accompanying us, and thank you. Gracias.